Okay, so welcome to the third class or week 3 tutorial sessions for this thermal physics course. And as you have already seen from the lecture videos, as that this week's lecture content is mostly based on. Let me choose the pen and start writing. So this week's lecture content is mostly based on 3 topics. So these are first of all, the topics can be broadly termed as what do I say? There is one aspect that is the thermal conduction part, and then there is this transport phenomena, right? So that is transport phenomena, and there is also this thermal conduction physics going on. Okay. So basically, you have 3 main aspects of it. So I am basically summarizing these in a bullet point first, so that when we discuss about the assignment problems, it will be better for us to categorize that what topic is it related to, and how to approach that problem exactly. So we have viscosity. The coefficient of viscosity is the coefficient of viscosity we term as eta. And then we have that there is thermal conductivity, which is given by this symbol K, and then there is diffusion coefficient, which is given by this constant symbol D, right? So you have these 3. Now most of the problems that we will deal with will vary with, like say these 3 quantities have separate expressions, and also they are related to each other by some way. Then you will see in some means you will also find relation with these quantities with the earlier learnt concepts that are mean, free path, etc. So collision, cross section area, etc. So all these things, how they relate to each other, and the main connecting formulas in between them, so that when you are given a quantity, you can use that and calculate the other unknown quantity. So these are the main things that we'll be focusing about in this week's assignment. Also now, to like state these things properly in a sentence, we can say that main concepts are that viscosity is basically this happens because of sorry, this is extra. Yeah, so this happens because of the velocity gradient among the molecules in a gas. So whenever there is a velocity gradient, del u, if you say the velocity is u, so du dx, let's say different position velocity is different, then in that sense you will have a momentum transfer, which is actually quantified basically by this viscosity coefficient eta, right? And then you can say that viscosity is somewhat like the resistance to the flow of a fluid. So it acts like that. It basically is related to the momentum transfer, and it is happening because of velocity gradient present in the system. And then there is this thermal conductivity. As from the name itself you can see that this is linked to the transfer of thermal energy. So in this topic we are concerned about transport phenomena, right? So some kind of transport is going on, like say in viscosity the momentum is getting transported, you can say. Then thermal conductivity is basically thermal energy transfer, and this happens obviously because of temperature gradient. So whenever there is one part of different higher temperature and another part of a lower temperature, then you know that the natural tendency is that from higher temperature to lower temperature there is a transfer of thermal energy or heat, and that is what mainly quantified by this term thermal conductivity, which actually specifies what amount of thermal energy is getting exchanged per unit area and per temperature gradient. Similarly, diffusion is also a transport of molecules, and it basically quantifies the molecular flux that actually gets transferred, and this happens because of the concentration gradient at different points. Like say, if one part has higher density or concentration of molecules compared to the other parts, then the natural tendency will be that the molecules will get transferred from high density part to low density part, and so the molecular flux will get transmitted, molecular flux that will get transmitted per unit area and per this gradient of density, that is quantified by the term diffusion coefficient. So these are the main factors that will come many of the times in all these problems. These are the main three factors, and they can also be related to the other previously known factor, which is the mean free path lambda. And you know, mean free path is just directly related to this sigma. Sigma is the diameter of a single molecule, and it is also the radius of the collision cross sectional sphere that you can imagine. So it helps you to calculate the collision cross section area between the molecules. So this is one thing, and then yeah, I think this will be the main thing that we'll be needing. And then these three quantities and how this is related to this and all the connecting formulas, using this all the assignment problems will be based on, right? So let us start then. We'll start from question 1. So initially the questions will not be very difficult. Anywhere none of the questions are much difficult, because as I said, these are mostly based on conventional formula, and basically you have to know the linking formula between these quantities and you will be done. Right, so let us start with question number 1. It says that determine the mean free path of air at STP, standard temperature and pressure, given that viscosity eta is given by this term quantity 1.7 10 to the power minus 5. This is the SI unit of viscosity, Newton second per meter squared. So you can see this is Newton means force, unit of force. Then second is basically time, right, and meter square means it is area unit, right? So what you get is that force into time per area. So as I said that viscosity mainly denotes the like basically it promotes the force per unit area and per unit velocity gradient. So velocity gradient means, let's say your velocity is u, then it is du dx, right? So what does it give you? So you can say force by area, keep it as it is. Then du dx, if you decompose it, you will get velocity means length per time or always, and then you have another dx below, so you have 1 by length. So this length dimension actually cancelled out, and you get ultimately force into time per area. So this is what the unit is. This is actually what I suggested that viscosity should be. So this is viscosity in SI unit. Then the mean velocity or the average velocity, this also you know from the idea of kinetic theory of gases, the very first week's assignment or very first week lectures you can follow, that this is the average velocity C bar of the gas molecules, which has a formula. You perhaps remember that it is 8 root over 8 kT by pi m if it is a single molecule, and for a single molecule. And you can also write it like root over of 8 RT by pi capital M when you are talking about 1 mole of the 1 mole of that element. So for a single molecule, small m is mass of a single molecule only, and therefore you have this K is not thermal conductivity K, do not confuse with that. So because this time we have K already assigned to thermal conductivity, so all the time I have to use Boltzmann constant, I will use the term KB instead of K. So you also so whenever I am sometimes I may also write KB as K, so please understand that Boltzmann constant is different and thermal conductivity is different. So if that happens sometimes, then please be conscious about it, that right now I mean to say KB is the Boltzmann constant, K suffix K subscript B. Sometimes people also write it as K also, but because we have another term standard K is denoted for thermal conductivity in this case, so to avoid degeneracy we will write KB for Boltzmann constant. Okay, And whenever you are not you're not considering just a single molecule but 1 mole amount of the whole gas, that means on that many number of molecules that are present in 1 mole, which is the Avogadro number, you are considering as a whole, then your average velocity formula will be root over 8RT by pi capital M, where R is the universal gas constant and capital M is the atomic weight of that means weight equivalent to 1 mole of the gas. So basically these are equivalent terminology. However, this is in also SI unit, so this is meter per second velocity. And then density of the molecules means this is mass density, because you can see this is 1.29 kg per meter cube. That means you have SI unit, this is mass by volume, so this is the mass density rho. So basically you have to calculate the mean free path of air, lambda of air at standard temperature and pressure, which is a known value, because you know if STP or NTP is mentioned, you know what is the standard temperature and pressure value. So this is also known to you. So first collect what known informations you have. So you have known information about T, P, then viscosity coefficient neta you know, average velocity c bar you know, and rho the mass density you know. Then you have to determine what is lambda, right? So let us choose the blank page and start to solve it. So as I said, it will be a very straightforward sort of a solution, because all you have to do is to choose the right formula and follow the steps. Okay, so first of all, because there is a term viscosity, so viscosity, as I said, eta is the tangential, or let's say I am not going into the definition part anymore, because you can look at that from the lecture itself. So I'll directly write down the formula. So eta is equal to 1/3 rho c bar lambda. Okay, so this is the formula already derived in the lecture for viscosity. You can see that from there how this is how you are getting that, but this is the standard formula for viscosity, where rho is mass density, that means mass per unit volume of the gas molecules. C bar is the average or mean velocity, and lambda is your mean free path. That means it is the average distance that the molecule travels in between two successive collisions in a straight line path. Okay, so basically now we can already see and look at the formula, that if I just mark them accordingly, so you have this information about rho present in your question, you have c bar also given in the question, then you have also lambda, lambda is something that you have to calculate from there, but eta you already know from the question. So from this equation everything is known except for this term lambda, which is your mean free path, and this is we have to calculate, and all these three other terms are known to you. So this is a very straightforward problem, as you can see. So we'll do exactly that. So lambda is equal to then just 3 times eta divided by rho c bar. Okay, so if that is the case, then just put the values carefully, maintaining the units all to be same. So if you are choosing SI units, then every term should be in SI unit, and just calculate it to get the final answer. So you have eta as 1.7 into 10 to the power minus 5 into all SI units, 1.7 10 to the power minus 5, and then 4.5 10 squared and 1.29. Remember, all are in SI units, so I do not need to convert anything. So 1.7 10 to the power minus 5, 4.5 10 square and 1.29. So this is 1.7 to 10 to the power of minus 5. 4.5 into 10 square is the c bar term, and rho is 1.29. So this is So just verify once if I have taken all the terms correctly. And then for the unit, you already know lambda's unit because it is a length scale. So I mean mean free path is a length scale, so it will be in meter. But you can also check from the separate units conversion that this formula is actually giving you the right dimension. So like say Newton second per meter square, if you take the viscosity as, so it was in the top part, so it is Newton second per meter squared. Then you have rho, that is kg per meter cube, so this is 1 by kg by meter cube. Then you have c bar, which is simply a velocity, so it will be just meter per second. Now this meter square and meter makes meter cube, this cancels out, so you have second and second will go up, so it will make second squared basically. So Newton into second square per kg. Now you know that Newton is the force unit and force is nothing but mass times acceleration. So you have mass kg times acceleration means length by time squared, right? So this is meter per second squared into second square. So this is all automatically cancelling out. Then kg, so this kg and kg cancelling out and giving you meter. So dimension wise also this formula is right. Now just do the calculation. So you have 3 into 1.7 into 10 to the power of minus 5 divided by 1.29 into 4.5 into 10 squared. So you have 8.78 10 to the power minus 8 is what I am getting right now. So let us check and go back. So we had 8.78 10 to the power minus 8. So if we have this option number C, right? 8.78 10 to the power minus 8 is the correct answer. So we are getting that exact answer and it is in meter value. So your option number C is correct, right? So this is done. Then we go to question number 2. It is saying that the thermal conductivity of a gas at a temperature T is K, right? That is a basic symbol of thermal conductivity. And it is asking at what temperature the thermal conductivity is doubled. So basically if you look at the problem in this manner, that you have a temperature T, thermal conductivity is equal to K. So let's say if you take this as condition number 1, then you have, let's say we denote T1, that means the case 1 temperature as this temperature, this is T, and correspondingly the thermal conductivity at the temperature we denote by K1 and that value is given in the question as K. Okay, now we say there is a we now say that there is a different temperature that we are now talking about. Let's say this is T2 and let's say at T2 the thermal conductivity is K2. Okay. So if that is the case, then what was the question? That I think at what temperature the thermal conductivity is doubled. That means it is already asking you to take your K2 as doubled of the earlier case, that means 2K. So if K2 is 2K, then what is the temperature for that? What is T2? So basically you have to find some connecting formula or some connecting relation between thermal conductivity and the temperature, and then you have to use this condition that at case K1 was K and K2 is 2K. So then if T1 is T, then what is T2? So you have to get the value of T2 something in terms of T. Okay, so that is your main idea. So basically find a connecting relation between K and T. So this will be our first goal. So if you refer to the lecture notes, you will see that they have already provided you all the necessary formula. So I'll be directly using them without deriving it thoroughly. So your K has a already pre-derived formula as 1/3 in C bar lambda CVM. Okay, let me define the terms what are present here separately. So here N is your number density of molecules, that means number of molecules per unit volume. Okay, this means per volume. Then you have C bar is the average or mean velocity. Then this lambda is again the mean free path of the gas molecules. And this CVM is interesting, that whenever you have this CVU means that this is the specific heat at constant volume, because you know for ideal gases there is one specific heat as CV and other is as CP. So this means subscript V means this is at constant volume specific heat, and subscript P means this is at constant pressure specific heat. So see here CV means this is constant volume, but then what is this superscript M term meaning? So whenever there is this, so it means the mass specific heat at constant volume. So what do I mean by mass specific heat? So generally the standard specific heat that we talk about or we use in the ideal gas expression like Cp minus Cv equal to R for 1 mole of gas. So there, because this is predefined for 1 mole of gas, okay, so this is basically molar specific heat. That means this is the specific heat corresponding to 1 mole of the gas. So these are all molar specific heat. Whenever there is nothing mentioned other than only Cp or Cv, you assume that this is the standard expression for molar specific heat, and because it is V, so this is the molar specific heat at constant volume, and similarly C subscript P will be just molar specific heat at constant pressure. Okay, and nothing else. So this is molar means this is for 1 mole of the gas, right? But whenever you have just CVM, it means that this mole m means this is specific heat at constant volume but for a single molecule. But only for a single molecule that has a mass m, right? So if that is the case, then you have this formula also, that 1/3 n C bar lambda CVM is K, right? Then you can use the expression of lambda also, because you know the mean free path formula from the earlier week lecture. This is just root over 2 n pi sigma squared, where n is the number density again, and this sigma squared, where sigma is the diameter of each molecule. And all in all, it is also the radius of the collision cross-sectional sphere that you can imagine for a single molecule. Whenever it is passing through the whole system of molecules, it is bound to collide with the surrounding molecule. So you, for simplicity, you simplify the system, or you simplify the phenomena like say only one molecule is moving and all the other molecules around are frozen at their position, as if. So this is not the real case, this is just a simplification of the scenario, so to understand it better in simpler terms. So if you assume that, then what will be the case is that the moving molecule is passing through the frozen sea of the other molecules which are also identical, only that they are frozen at their positions. So now whenever this moving molecule comes in proximity of another molecule, where their center to center distance is exactly sigma, because radius of each is sigma by 2. That means this is one molecule of radius sigma by 2, and it collides with another molecule head on head, let's say. So the maximum center to center distance between them, because this is also identical molecule, so it is also radius sigma by 2. So their center to center distance, if you look at, it will be total of sigma. So as if this whole thing is forming one collision cross sectional circle, I'll say. Sorry, this has got messier, but yeah, that was what I am saying is that, so basically you can then imagine like this whole thing around this is a collision cross section area that is equivalent to a circle. Okay, and that circle has a radius of so basically this circle has a radius of sigma. So yeah, so the thing will be like, no, it's okay, but just that the drawing is not very accurate, so just try and understand what I'm trying to explain here. So this whole thing is then sigma, and this whole thing is also then sigma. So this in between thing is also sigma. So just try to get the idea that it has a radius of sigma. Then the area of that circle will be simply pi times sigma squared, because it's the radius then, and this is the effective collision cross section area, because whatever molecule comes inside this area will have the probability, or the maximum probability to get have a collision with the other molecule. So this is the effective collision cross section area, right? So if that is the case, then so where were we discussing? So basically we needed to simplify this formula so that we can get a direct connection with of K and T. So let us get into that business. So K was our 1/3 in C bar lambda CVM. Now we know the expression of lambda, so let us use that, put that into this equation. So this is 1 by root over 2 n pi sigma squared. So this n and this n cancelling out, and this is CVM. Okay, so this is CVM. Now you have whatever it is left is that C bar CVM divided by 3 root over of 2 pi sigma squared. Now look at this very carefully. Okay, first of all, for your convenience, you can also convert the CVM into the standardly known CV. So how to convert CVM to CV? How to convert? Because this is more standard, because we already in real practical applications we mostly deal with the molar specific heat, because that is more standardly known rather than taking the specific heat of each molecule individually. So molar specific heat, so this is, you are going from a single molecule to number of molecules that are present in 1 mole. So this is single molecule, and this is all molecules present in 1 mole of the gas. And you know the answer, that it is exactly the Avogadro number, or Avogadro number, which is 6.023 into 10 to the power 23. This is also a universally known constant. So this much number of molecules, all of them combinedly has a specific heat of CV. So basically to go from CVM to CV, the calculation is simple, that from a single molecule to this amount of molecule. So you just simply multiply by Na. So CVM times Na is equal to your CV. This is the formula. So you can also directly use it here, that C bar. So if you convert into CV, that means you have to also multiply it by Na and divide it by Na. Because multiplying by Na you can convert into CV, then you have to also compensate for that, so you have to divide by another Na. Or rather you can think of it like, you just simply substitute CVM as CV by Na. So here it will be C bar CV to 3 toward 2 Na pi sigma squared. Okay. Now look at it carefully. That what are the terms in this expression which are dependent on temperature? Like say this CV. CV is a standard molar specific heat at constant volume. But if you ask from your earlier knowledge that does CV depend on temperature? So, although in real practical cases CV does have temperature dependence, C in fact does have temperature dependence, but because we are talking about ideal gases, right? We are dealing with kinetic theory and ideal gases, so ideal gases always has some idealized assumptions, because of which this specific heat will be temperature independent. I think you have already studied it in the very first week's lecture content from the kinetic theory aspect, that from kinetic theory of ideal gases, CV is temperature independent. Okay. So, because you know that CV is simply du dt, which is the temperature derivative of the internal energy. Okay. And for internal energy, we used to take the equipartition theorem for the energy. So there we found out, we knew that by equipartition theorem we can say that the energy of a system is distributed such that per molecule per degree of freedom it will be half kT, right? So by that sense, if there are f degrees of freedom, it will be half kT times f, and for in a number of molecules, n number of molecules, it will also be multiplied by a n factor. But so basically u is then linearly dependent on T. So whenever you have this linear dependence, and then again you are taking a temperature derivative in CV, so that linear term also goes away and you have just some term that is independent of temperature. So from classical concept of energy equipartition theorem, energy per molecule and per degree of freedom, short DOF, is equal to half kT. So for n molecules and f degree of freedom, it will just be simply multiplied by both f and n. Okay. Or rather, if you are considering 1 mole, then there will be Avogadro number of molecules, which is Na number of molecules. Then it is half kT f Na. Then it will be half Tf. You know that k times Na. So here this is again, this is Boltzmann constants k, not thermal conductivity k. So sorry for the confusion, but this is, I am rectifying it so that please do not get confused with this and thermal conductivity. So this is Kb times Na, and you know that this is basically the universal gas constant R. So you are simply getting half FRT as your U from equipartition. Then if you have CV, CV is just a temperature derivative of this linear dependence term of U. So this is just half FR, right? Because the derivative is taking away the linear term in T. So this is temperature independent then. It is a term that is nowhere dependent on temperature. So one is eliminated out of the option, that from this expression of K, the CV term has no temperature dependence. Okay, so let me not cross out this because then it will be difficult for you to see. So let's say this is out. So I am putting a small cross mark on the top of it so that you can guess that okay, this is temperature independent. This has nothing to do with temperature. Then you have 3 root 2 is constant, so it is obviously gone. it should not have. Then same with pi, constant terms does not have any parameter dependence. Then Na is Avogadro number, which is also a standard constant, so this is also no temperature not temperature dependent. Then there is sigma. Sigma is nothing but molecule diameter, right? And that should not depend on temperature, especially even if it does somewhere, but at least for ideal gas assumptions there is nothing mentioned as such that sigma should depend on temperature. So this is diameter of molecule, so this is molecular diameter, and hence it is independent of temperature. So only term that you are left with is this C bar term. This is the average velocity term. This I have kept for the left because you can already guess that C bar does have a temperature dependence. In fact, this is the only term in here that has a temperature dependence. Other than that, all the terms present in K has no temperature dependence. So C bar has a root over T temperature dependence proportional to root over of T, and because K is proportional to directly C bar, since K is directly proportional to C bar and C bar is directly proportional to root over of T, hence you can combine them and you can get that your K is directly proportional to root over of T. This is what should happen. So you are getting this relation, that the relation between temperature and thermal conductivity is that K is directly proportional to root over of T or square root of T. Sorry. Yes. So your K is directly proportional to root over of T. Then as the question was being asked that K1 is the thermal conductivity at T1 and K2 is the thermal conductivity at T2. So then by this you know that if this is the relation, then you will have K2 by K1 is equal to root over of T2 by T1, or you have T2 by T1 is equal to K2 by K1 whole squared, or you have T2 equal to T1 times K2 by K1 whole squared. Now you know why I am only structuring it in terms of to get the formula for T2 only, because I am doing this because you have to calculate T2 from here. Other values are given to you. Like say you are told that T1 is equal to temperature T and K1 is equal to thermal conductivity K. Then they said if K2 is double, that means K2 is 2K, then what will be T2? So your T2 is basically T1 is T, so put all the values together, then K2 is just 2K and K1 is K, 2K by K whole squared, this is 2 squared, that means 4T. So you have T2 value calculated from the question, T2 is equal to 4T. So let us find out the answer, that temperature will be 4T. Okay, so option number D will be correct. Right, so this is also done. So we have covered 2 questions. Then we have question number 3, which asks that calculate the radius of an oxygen molecule if its coefficient of thermal conductivity K is given by this term 24 into this thing at 0 degree centigrade, and specific heat at constant volume Cv is given by this term. So you have to calculate the radius of that molecule, right? So just 1 second. Okay, so let us continue where we left off. So we are discussing problem number 3, which says that calculate the radius of an oxygen molecule if its coefficient of thermal conductivity is K, that is given at 0 degree centigrade, the temperature is given, we have to convert it in Kelvin, and the specific heat at constant volume is some value joule per kilomole into degree. So just notice that here it is given per mole or kilomole in this case. That means this is a molar specific heat. So you have to identify that first, even if it is CV written, but you have to reconfirm it from looking at the units first. So this is the specific heat at constant volume, which is a molar specific heat. Okay, that is a standard one. And you have information about K, the thermal conductivity. Also you have information about the temperature T, and you have to know what is the radius of the oxygen molecule. So first of all, as I said, you have to identify what formula you need to use. So in this case, you have no other option other than using the conventional, first use the conventional relation that you know about the formula for thermal conductivity. So you know the expression of thermal conductivity. I am going to write it down again. So thermal conductivity is K equal to, it is written that it is 1/3 N C bar lambda CVM, where CVM is specific heat at constant volume for a single molecule. Okay, for a single molecule, right? And if you have to write it in terms of the standard specific heat at constant volume, that means molar specific heat. So if you have to write down molar specific heat, that is only CV. So you have to simply multiply this CVM term by Avogadro number, that is 6.023 10 to the power 22, which we write down as Na. So here you know that if you here adjust the terms, like you multiply Na and divide it, to adjust you divide also by Na term. So what you get is this kind of a thing. Now because you can separate these two terms out, look at it separately, and this is just N C bar lambda by 3 Na into Na. CVM is just your standard capital CV, which is the molar specific heat. So basically you are getting a K equal to 1/3 N by Na into C bar lambda CV. Now remember that in the question you are given the values of K, then you have been given the value of the temperature from which you can get the specific heat, sorry, not the specific heat, but the the average velocity, because you know the formula, and also you know the system, so you know the mass. So in this case I think it was given as what was the system given? Let me check one second. So it was oxygen or yeah, oxygen molecule. So you know the mass, etc. So you can directly get the velocity value also. Now because you know all those informations, and what are left, so basically sorry, so temperature given, K given, and the CV, this value is given. Okay, so you know everything except you do not know this this lambda, right? So we can further simplify this term to write down in a different form, that you write it down as N by 3 Na into C bar into lambda, you can write down as root over 2 N pi sigma squared into CV as usual. So here this N and this N cancels out, this is the number density, and this sigma is the diameter of each oxygen molecule. Okay, so this is just K equals C bar by 3 root over 2 into CV also 3 root over 2 Na pi sigma squared. Okay, so basically you have this formula, and then so you have to get this value, right? Because I think they ask for the radius of oxygen molecule. So you, if you know sigma, that is the diameter of oxygen molecule, you can just simply divide that by 2 and get the radius idea, right? So you can take sigma out from this equation as sigma equal to C bar CV by 3 root over 2 Na times pi times K. Now because this was sigma squared, so you have to take additional square root to get sigma. And then once you have got that, you just have to put the different values for these known terms. So first of all, we have not yet calculated what is C bar, so let us do that first. C bar is equal to simply root over of 8. Yes, so C bar equal to simply root over of 8 KT by pi m. Sorry, this should be KB because this is Boltzmann constant. Now this is 8 into 1.38, all SI unit 10 to the power minus 23 into 0 degree centigrade means 273 Kelvin. So here it is mentioned in the question that T is equal to 0 degree centigrade, which is just 273 Kelvin. Okay. So this is 273 divided by pi into mass of a single oxygen molecule is, so the atomic mass of oxygen molecule is simply known that it is 32 grams. So each oxygen molecule has a mass of equivalent to 32 atomic mass unit or AMU. Or if you want to convert it into grams, so it will be, for each molecule it will be 32 gram divided by the Avogadro number, which is 32 into 10 to the power minus 3 kg divided by 6.023 into 10 to the power 23. Okay, so this is M. This is M. 32 10 to the power of minus 3 divided by 6.023 into 10 to the power 23. Now if you just take your calculator and calculate this, that what is the average velocity value coming out of this, so it will be 8 into 1.38 into 10 to the power minus 23 into 273 divided by pi into 32 into 10 to the power of minus 3. Then take this on top, so into 10 to the power 6.023 10 to the power 23. So we are getting around, this square root is giving us around 424.9 meter per second. So this is the average velocity or mean velocity of the gas molecules, 424.9. So if that is already known, then you know the other terms, so we just directly put them from the question itself. So C bar is just 424.9 to, so yeah, so this was 20.9 10 to the power 3 joule per kilomole degree. 20.3 10 to the power 3 joule per kilomole degree. So yeah, so this is 424.9 and then you get sorry, not CV here. CV here is value is given as 20.9 into 10 to the power 3 joule per kilomole degree. So first of all, because it is kilomole, so this is 20.9 into 10 to the power 3 joule per 10 to the power 3. So this will be like C bar is 20.9, this is joule per mole degree. Now if you just write it down, that it is 424.9 into then 20.9 in SI unit, 10 to the power 3 and minus 3 cancelling out here, so we will not write that, divided by 3 root over 2 into pi 6.023 10 to the power 23 into, so this is 3 over 2 pi n into k is k value is I think given in the question, right? So k is basically 24 in 10 to the power minus 3 joule per meter second degree, 24 in 10 to the power minus 3 all SI. So we'll just try to calculate if this is coming or not. 424.9 into 20.9 divided by 3 into root over 2 into pi into 6.023 into 10 to the power of 23 into 24 into 10 to the power of minus 3. This is the case, then square root is simply 2.14 into 10 to the power of minus 10. Radius of oxygen molecule is just diameter by 2. Then it is 1.07 into 10 to the power of minus 10 meter, or it is somewhat 1.07 . This is 1.07 angstrom. This is radius of okay, so let us check whether this was an option given in the question. So we have calculated 1.07 angstrom. So this is the exact value that is given here. So this matches. Okay. Now, so this question is done. Okay. So question number 4 is the coefficient of cell diffusion of oxygen at 273 Kelvin and 1 atmosphere pressure is 1.8 into 10 to the power minus 5 meter square per second. So then estimate the mean free path. Now till this problem we are only dealing with the viscosity coefficient and the thermal conductivity, but for this particular problem we have a new term which is the coefficient of cell diffusion, which we denote by D, which I already had written earlier, that this is the this is coming because of the diffusion of the molecular flux, and the measure is that this is the molecular flux flowing per unit area and per unit concentration gradient, because this flux flow happens because of the different difference or gradient of concentration at different parts of the gas, right? So you have to use the formula for D for solving this problem. Now also you have been given the information about temperature T and the pressure P, and the value of D is given, and you have to estimate what is lambda. So let us try to solve it then. So question number 4 is that you have so you have first of all let me write down what is the formula for D. So here you can see from the question that you have to find out some connection or some formula that connects the self diffusion coefficient D with the mean free path lambda, because that is what you need to calculate here. So there is a formula given in the lecture, you can find it, that it is 1/3 C bar lambda. where c bar is same, the average velocity for the molecules, and lambda is the mean free path. Now c bar, you know that this has a particular formula, that this is root over of 8 kt by pi m. This is for a single molecule, not molar or anything. This is for a single molecule. And if I have to take the quantities correctly, so first of all, remember this is given in the question, that this is a oxygen gas that they are talking about. So oxygen is has a diatomic molecule that you have to know and take the mass accordingly for that oxygen. Temperature is 273 Kelvin, and this D is 1.8 10 to the power minus 5 meter square per second. So our D is, so 1 second, so let us write down that D is 1.8 into 10 to the power minus 5 meter square per second. Okay, so if this is not properly clear, so let me write this again. So this is your C bar. Okay, so now this is a oxygen gas, which is a diatomic molecule. That means single molecule has 2 atoms in it. Diatomic molecule. Now see correctly that you have this D value known in the question. You have to take out lambda. So then you have to know C bar also. Otherwise you cannot calculate lambda from this formula. So C bar, for this C bar you have all the information, because you have temperature as 273 Kelvin, and you will know the mass of oxygen, that is standard, right? So you know that oxygen has a atomic weight of 32 gram. That means this is 1 mole of oxygen equal to 32 gram, right? So 1 mole has n number of molecules. I don't need to repeat it every time, but you probably understand that n subscript A means the Avogadro number constant. Okay, so this is Avogadro number of molecules, or n number of molecules have total mass of 32 gram. So if that is the case, then for a single molecule, then for one molecule, what will be the mass? It will be 32 gram by Na. Okay, that means it is 32 by 6.023 into 10 to the power 23, and this is gram. Okay, so we have to use this in the position of m in the C bar expression. So, and this is this is Kb. So this is Boltzmann constant. So our C bar will be, first let us calculate C bar. 8 into, this is SI unit 1.38 10 to the power minus 23 is the Boltzmann constant value, into temperature is 273 Kelvin, divided by pi into m is 32 by 6.023 into 10 to the power 23. Now let us calculate this first. So you have the numerator, you have 8 into 1.38 into 10 to the power minus 23 into 273 into 6.023 into 10 to the power 23, right? And then you have 1 divided by pi into 32, and the whole thing is under square root. So then it is giving you 13.444 almost meter per second. This is the average velocity. Now once you know this, so you use D is equal to 1/3 C bar lambda. That means your lambda will be 3D by C bar, right? So now D value is given in the question, that it is 1.8 into 10 to the power of minus 5. 1.8 10 to the power minus 5 by C bar will be 13.44, right? So you have 3 into 1.8 into 10 to the power minus 5 divided by 13.44. So we are getting, if I have done the calculation right, we are getting 4.02 into 10 to the power of minus 6 meter, because it is a length scale, so it will be in meter. So let us check whether it matches or not. Yeah, so this option number D has I think there has been some mistake in the calculation. Let me check just. I think the velocity calculation has some error. Alright, so I have done a mistake that I have to change this into kilogram and not gram. So that is a mistake I was telling you about, that you have to always make sure that everything is converted in SI units or in a similar unit. Otherwise you will have problems in the calculation. So this will not be gram anymore, but we have to, because we are taking everything in SI, so we have to convert it into kilogram, right? So if this is in kilogram, so this is 10 to the power minus 3. So let me then calculate once again. So it is root over 8 kT by pi m, where T is 273 Kelvin. So this is 8 into 1.38 into 10 to the power minus 23 into 273. Okay, divided by pi into 32 into 10 to the power of minus 3. Okay, and then this 6.023 comes up, so 0.6.023 into 10 to the power 23, and then the whole square root gives you, okay, so the velocity value itself came different because I had a problem in the units. So please correct this. So this is 424.9 meter per second. Okay, so once you use this in this expression, this is 424.9, almost 425. Then you have 3 into 1.8 into 10 to the power of minus 5 divided by 424.9, which is like 1.27 into 10 to the power of minus 7 meter. This is your lambda. Now you can see that this matches with your questions given option, that is your option number A. So this is done. Then let us move on to question number 5, where it is asked that a molecule of methane has a molecular weight 16, can be considered as a sphere having 5 times the volume of an argon atom, which has a molecular weight of molar. Sorry, this is not molecular weight, they mean to say molar weight. That means the weight for 1 mole of that particular element. That means 1 mole of methane has 16 gram of weight, and then 1 mole of argon has 40 gram of weight. Again, remember that while doing the calculation you need to convert it into kg. Okay, so however for methane it is considered, the molecules are considered as a sphere shape. Okay, so the geometry is taken as a sphere for the molecules, and it is said in the question that for methane the volume of that sphere is 5 times the volume of the argon. So then what would be the ratio of the viscosities of methane and argon at standard temperature and pressure? Okay, so let us choose a blank page and start solving this. So first of all you have a methane molecule. Okay, and second is you have a argon molecule. Now for methane you have been given that the molar weight is equal to 16 gram for 1 mole, and for argon the molar weight equal to 40 gram for 1 mole, right? Also assume that assumption is given in the question itself, the gas molecules have shape like a sphere. Okay, that means if you consider that, let's say we identify the radius of the methane molecule as Rm, right? R subscript m. So it is the radius, m for methane, radius of one methane molecule. Why we are taking radius? Because we have already taken the assumption that the molecules are shaped like a sphere. So sphere will have a radius. So that radius we considered that Rm is the radius of the methane molecule, and Ra is the radius of argon molecule, right? Also we also take that then Vm, which is the volume for methane molecule, because it will have a volume of a sphere. So this is 4/3 pi Rm cube, and volume of argon molecule is 4/3 pi Ra cube. Okay, so this is the simple volume formula for the sphere that we have taken. And another information given in the question is that the volume of the methane molecule is 5 times the volume of argon molecule. So this is given in the question itself. Okay, right. So then if that is the case, so we can also from this take out what is the radius ratio for these two cases, because we can we can write Vm as 4/3 pi Rm cube, and this is equal to 5 times the volume of argon, so 4/3 pi Ra cube. So this 4/3 pi cancelling out from both sides. So then you have Rm by Ra whole cube is equal to 5. Then you have Rm by Ra is equal to 5 to the power 1/3. Okay, so Rm by Ra is equal to 5 to the power 1/3, this ratio. And then in the question it is asked that what is the ratio of their viscosity coefficient or eta. So you know that eta is the coefficient of viscosity, and which has a formula that it is 1/3 rho c bar lambda. Okay, now so from here we have to calculate what is the ratio of eta m by eta a. That means what is the ratio of the methane molecule's viscosity by the argon gas's viscosity. So we have to make use of this formula, and only information we have known is this information, and also from the atomic molar weight that they have given to us in the question, we can also calculate the mass ratio for a single molecule, of course. So let us calculate that too. So what is this is the radius ratio. Then what will be the molecular mass ratio, means mass of a single molecule. Let us also calculate that, because this will be needed. So it is mentioned that the molar weight of methane is equal to 16 gram, right? 16 gram, right? So that means your mass of a single molecule for methane is equal to 16 into 10 to the power minus 3 kg divided by the Avogadro number Na, because you are already familiar with that concept, how to convert from molar weight or atomic weight into mass of a single molecule. So I will not go into that again. And the mass of argon molecule, then again same, mass of an argon molecule, this is equal to 40 gram was given, so 40 into 10 to the power minus 3 kg divided by again the Avogadro's number. So what is the ratio then? M subscript M by M subscript A is equal to just 16 into 10 to the power minus 3 by Na into then ratio for Na 40 into 10 to the power minus 3. So this and this cancelling out, you are only left with 2 by 5 is the ratio. Okay, so we have done the mass ratio and we have done the radius ratio. Then directly jump into this. So you have in here, you have what do I say? So first write this down. Rho is basically m times n. M is the mass of the molecule and n is the number density of the molecules, means number of molecules per unit volume. So this product of m and m into n gives you the mass of all the molecules given present in unit volume, that means the rho mass density. So you can decompose it like m into n, and then c bar is just the average velocity. So you also know that formula for that, root over 8 kbt by pi m, where m is mass of a single molecule, into lambda is basically, so lambda is mean free path, that formula you also know. So root over 2n pi sigma squared. Here n and this n cancelling out. Okay, so just now try to see what are the parameters that you are left with in here which are different for argon and methane. So like here you can see, this is, first of all, this is m by 3 root over 2 pi, and remember that this sigma was just molecular diameter in the standard expression for mean free path. So this is molecular diameter. In our case, because we have taken the molecular radius as capital R, which is capital R m for methane and capital R a for argon. So this sigma, okay, so this sigma for methane will be just 2 times the radius of methane, and sigma for argon will be again 2 times the radius of argon. This is the diameter of the two molecules, because you multiply the radius by 2 to get the diameter. And then what are the other terms? First let me separately write out the constant terms, which has nothing to do with the parameters. So these are the constant terms, and then you have this, so take, no, do not write m here because m is not constant, m will be written as a parameter. So this m up and this root over m, giving you root over m only, and you have also the root over t from here. Okay, and then you have another parametric term which is this sigma squared. Okay, so you can see that the term in the front that I have separated, these are all constant terms. Okay, this has no parametric dependence, and these will be same for both methane and argon. Also, one thing you notice that this root over t, although I have written it in the parametric part of the expression, but actually because for both the gas molecules the pressure and temperature has remained fixed, because they have mentioned STP. So that means both gases are in STP or standard temperature pressure. That means T is fixed at 300 Kelvin for both, and pressure is also fixed at 1 atmosphere for both. So that means T does not change for both of them. So T is constant here for both the gas molecules. So T will not have the parametric dependence, but T can go here in the constant term part. So what we will do is that, because T does not vary for both the gases, so we will remove T from here and we will position T where it should be in the constant term only, right? So we are only left with this as your varying part of the expression of eta for different gases of methane and argon. So this information will be needed for us to take the ratio of eta for both the gases. So your eta of methane divided by eta of argon is equal to, so first of all, eta then is proportional to root over m by sigma squared. Okay, so if that is the case, then eta m by eta a will simply be root over of m by ma into sigma a by sigma m whole squared. Okay, so this is m by ma, and because you know sigma is just 2ra, and this is 2rm, and then whole squared, so this 2 and 2 cancelling out, this is just the radius ratio, and then the square of that. So we'll be needing the calculated values from earlier. So like here you have mass ratio m by a, for methane by argon it is 2 by 5. So here again it is methane by argon, so this is 2 by 5. Okay, square root of that. Okay, and then you have Ra by Rm. So you have calculated Rm by Ra, which was 5 to the power 1/3. So this is the inverse of that. That means it is 1 by 5 to the power 1/3 and then squared. That means 1 by 5 to the power 2/3. Okay, so you have then just calculate this, that this is your root 2. This is your root 2, 5 to the power half into 5 to the power of 2/3. Okay, so you will get root over of 2 by 5 first, and then into 1 by 5 to the power of 2 by 3. So we are getting 0.216 is your answer of the ratio of methane and argon's viscosity coefficient. Let us check whether the answer is matching. So here we have an answer. Here the answer is not written, but this is actually B. B is the correct answer. Alright. Then question number 6 is, the thermal conductivity of a gas assembly at temperature T is K at a given number density of small n. What will be the fractional change in thermal conductivity is the number density is increased 3 times. Okay, so in the question, first let us understand what they are asking. They are asking that your thermal conductivity is at temperature T is mentioned as K and number density is also given. Then they are asking for a dependence, if there is a dependence of the thermal conductivity on the number density N, because when the number density is increased 3 times, then they are asking what will be the change in thermal conductivity. So the basic idea is you have to find out whether there is any relation between thermal conductivity and the number density, and if there is a relation, then there will be a change is calculated accordingly, because if then the number density is increased thrice, then accordingly as per the formula K will also change. But if there is no dependence, then it will not change anymore, it will not change at all. So let us then find out whether there is a relation. Okay, so your question number 6 is that this is your what was that, K. K is the thermal conductivity at temperature T, and A is the number density of the molecules. Now K has a formula that K is equal to 1/3. You have used this formula before also. So 1/3 Mn C bar lambda not Mn, so 1/3 in C bar lambda and then CVM, which is the specific heat at constant volume for one molecule, not molar specific heat. And then when you convert this as N by Na into C bar lambda, then it is specific heat at constant volume for 1 mole, that is a molar specific heat. So this is your known expression for K. So at the initial glance you can see that there is obviously of course a independent part present. Okay, and that has a linear dependence, linear proportional dependence with K. But do not get misguided by it, because you have to still decompose the whole thing and finally see whether the N is there or not. So do not just get draw the conclusion from here yet that K is proportional to N or anything, because you still have other terms that can have independence inside them. So let us decompose all of them. Like say for C bar, you know there is no independence, because it is just root over 8 kVt by pi m. And for lambda, if you decompose, you will get a independence, that is root over 2 n pi sigma squared. And then again CV is just the molar specific heat at constant volume. You know that is a constant, it is temperature dependent, and mostly it has a form like, I think if your internal energy is given as half F RT into N for a number of molecules, then you have du dt is equal to CV. So then it is just half F R, or for, because we are talking about 1 mole, so there will be no N here, so this is just half Fr, where F is the degrees of freedom and R is the universal gas constant. So you know that this is a constant value like half Fr molar. This is the molar specific heat for 1 mole. So obviously this has no dependence on N. Only dependence on N comes from already present N and this N in the mean free path lambda. So this n and this n is cancelling out. That means your k is becoming independent of n. So k has no further independence. Okay, so k is independent of n. That is, even if n is increased 3 times, it will not change the value of k anyhow, because this is independent of n. No matter whether you decrease n or increase n or keep it the same, k will not be affected by any means. Okay, so this will be our answer for this question number. So this was a trick question. You can see that even if at first glance you will see that there is a dependence of k on n, but that is not true. Okay, so this answer will be none of the above. Now question number 7 is calculate the diffusion coefficient D of a hydrogen gas at 300 Kelvin and 1 atmosphere pressure given the mean free path lambda is equal to this thing. Okay, so you have to calculate the diffusion coefficient, and for hydrogen gas, which is a diatomic molecular gas H2, at temperature is 300 Kelvin and pressure is 1 atmosphere and mean free path value is given, then you have to calculate what is the diffusion coefficient. So first of all, let me solve this. So lambda, remember lambda have value is given as 17.91 10 to the power minus 8 meter. So lambda 17.91 to 10 to the power minus 8 meter. Okay, and temperature is 300 Kelvin, pressure is 1 atmosphere, and you know the diffusion coefficient formula, this is just 1/3 c bar lambda, right? Where c bar you can calculate separately by the formula known, root over 8 kt by pi m, and m you can know that because the hydrogen gas is given, that is mentioned in the question, and lambda is just 1 by root over 2. Sorry, lambda is value is already given, so you can directly use the value of lambda. Okay, so for hydrogen gas, for mass of a single molecule will be 2 into 10 to the power minus 3 kg divided by 6.023 into 10 to the power 23. Okay, so calculate this. This is kBT, of course. 1/3 into root over of 8 into 1.38 into 10 to the power minus 23 into 300 divided by pi into 2 into 10 to the power minus 3 by 6.023 into 10 to the power 23. Then this lambda is 17.91 into 10 to the power minus 8. And now cross check that everything in SI unit or similar unit. Okay, so this root over term is 8 into 1.38 into 10 to the power minus 23 into 300 Kelvin, and then this denominator term that comes up, it's 6.023 into 10 to the power of 23 divided by pi into 2 into 10 to the power of minus 3. Then the square root of this. Okay, so this is 1/3 into 1781.81 into 17.91 to 10 to the power of minus 8. So this you multiply by 17.91 into 10 to the power of minus 8 divided by 3. So you are getting 1.06 into 10 to the power minus 4, and because this is diffusion coefficient, is the value unit of meter square per second, because you can see the unit from here that it has only c bar and lambda. C is just velocity, so this is meter per second, and then lambda is again an length scale, so it is meter, so this is meter square per second. So this is your unit and this is your final answer. So again check whether this is correct. Yeah, so option number B is correct, and that is the accepted answer also. So this is also solved. Then question number 8 is about hydrogen gas is kept in two different containers at pressure and temperature different in both the parts of the container, which are mentioned as PA/TA and PB/TB. If PA, so this should be capital A. This is a printing mistake. So this PB is 8 times PA and TB is 4 times TA. Then what is the ratio of the diffusion coefficient? DB is to DA. So basically one container with two different containers with different pressure and temperature, and the ratio is mentioned. PB by PA is then 8 and TB by TA is 4. Then DB by DA you have to calculate. So let us try then. So this is problem number 8. So I'll draw two containers, container number A and container B. Now this has also gas filled in it, and container B also has gas filled in this. And this container has a temperature of TA and pressure of PA, and the second container has temperature of TB and pressure of PB, right? So also it is mentioned in the question that your TB is 4 times TA and your PB is 8 times PA. Okay, that means your TB by TA is equal to 4. So container number 2B has higher temperature and higher pressure because PB by PA is also 8. So these are mentioned from the question itself. Now we have to calculate what is dB by dA, where d is the diffusion coefficient. So d, we have also already known the formula for d in the earlier question as well. So d is simply 1/3 c bar lambda, right? So if that is the case, then either you can directly from here use this, or you can directly like use the formula for d. What will you choose to use? So basically P equal to NKT, that means, yeah, so let me just directly use the formula. That E is proportional to T to the power 3 by 2 by P. Okay, so right, just 1 second, so let me check something. So if I decompose this, then the C bar is just root over of 8 kT by pi m into lambda is root over of 2 pi sigma squared into n. And you know the pressure equation is P equal to N kBT. So N equal to P by kBT. Then this is just 1/3 into, take out the constant other parts, root over 8k by pi m into 1 by root over 2 into pi into sigma squared, and then it is root over of t divided by n is given by P by kBT. So take all the other terms which are constant and not varying parameters as separate. So this all throughout, I am not writing it anymore, but I am only focusing on the varying parts which are temperature and pressure in our case, because that is only different parameter for the two different containers. So these are unvaried part of the expression into this t comes up. So this is t to the power 3 by 2 and this is just P. So here you have the parametric part of the expression. Parametric means this is the quantity that is varied for both the container A and B. So from here you can get that if this is the unvaried part constant and this is the varying part, so then from here you can get that D is proportional to the power 3 by 2 by P. And here we use that. If that is the case, then dB by dA, this ratio will be simply TB by TA to the power 3 by 2 into, it is inversely proportional to P, so this is PA by PB then. And you know that TB is equal to, TB by TA is equal to 4 and PB by PA is 8. So here TB by TA is 4 to the power 3 by 2 and PB by PA is 8. So PA by PB is 1 by 8. Okay. So you have 4 root over 4 into 1 by 8. 4 root over 4 is 2 by 8. So this is 1 is to 1. So you are getting that the diffusion coefficient of both the container of gases has 1 is to 1 ratio. Okay, so let us check our answer. Okay, so this is the right answer. Even this is not, this part of the question is cut off, but this is the right answer. Right answer is D. Then question number 9. Okay, so question number 9 says that consider a container divided by a partition with a small hole. That hole has a diameter D and containing the same gas on each side. The gas on the left hand side has temperature T1 and pressure P1, and the gas on the right hand side has temperature T2 and pressure P2. If D is much smaller than the mean free path lambda, then the equilibrium is achieved by flux balance. In that case, at equilibrium, what condition do you get? So basically try to understand this problem. So in question number 8, you had two different containers having gases. Same gas, hydrogen gas, but two different containers. Now in problem number 9, you have been given that you have a single container, but that container is divided into two parts by a partition in between. Okay, but that partition is not fully separating the two parts, because it is mentioned that the partition itself has a small hole with a diameter of D. So you can understand that through that hole, gas molecules from one part of that container can travel to the other part. Okay, and similarly vice versa, that from the other side, that is right hand side to left hand side flow or left hand side to right hand side flow, both will be done through the hole in between in the partition. And it is mentioned that there is a particular temperature and pressure on left hand side, and as well as there is a particular temperature and pressure T2 and P2 on the right hand side. And another important condition is that D, the diameter of the hole, is much smaller than lambda or mean free path. And also when the system reaches equilibrium, it is mentioned that the equilibrium is achieved by flux balance. Okay, so even if it is explicitly mentioned, but even if sometimes it is not explicitly mentioned, you have to sorry, the screen froze, I think so. Let me give a minute. Okay, also check whether it is recording or not. Yeah, so it is recording fine. Okay, so as I was saying that, yeah, so even if it is not explicitly mentioned sometimes, but you have to understand from the type of the problem that the only possibility in this case is the no, sorry, there can be other possibilities as well, but like temperature exchange and anything etc. But in this case, they are explicitly mentioning that the equilibrium is achieved by flux balance only. So basically the molecular flux that can travel from left hand side to right hand side and vice versa. So when the flux are exchanged in such a way that the flux are balanced, that means flux from this side is equal to flux from the other side, then the system will achieve equilibrium. So that is explicitly mentioned in the question, and on that basis you have to get what is the condition of equilibrium for in terms of pressure, temperature, etc., and choose from these options. Okay, so let us now try to understand the problem and solve it. So this is question number 9. So first of all, let us draw a container like this, and in the container you have a hole in the partition. That hole is of diameter D. So this is part 1 of the container and this is part 2 of the container. Okay, so this is same container with a middle partition having a hole of diameter D. So on this side there is gas, on the other side also there is gas, and the pressure and temperature of the gases on both sides are different. That means here the gas is P1 pressure and T1 temperature, and on the other side the gas is P2 pressure and T2 temperature, and they have not mentioned anything that whether T2 is greater or T1 is greater, or P1 and P2 which one is greater. There is no explicit mention about those facts. Only because through this hole the molecules can traverse to the other side. So what will happen is that this gas from the right hand side, this is left and this is right, so from the right hand side some gas molecules can come to this side, right? And similarly from left to right also some molecules can go to the other side. Okay, so this red arrow means the molecules are traversing from right to left. Okay, and the blue arrow means the molecule that are traversing from left to right. Okay, so this is the molecular flux that is traversing from one side to other. So blue one is molecular flux from left to right side, and red one is molecular flux from right to left side. Okay, then let's say that the molecular flux from left to right we mention as phi 1, and the molecular flux from right to left we mention as phi 2. So phi from left to right is denoted as phi 1, and phi from right to left is denoted as phi 2, where phi means a molecular flux. Okay, right. So then your equilibrium condition is given, that condition for achieving equilibrium is that the flux, molecular flux flow from both sides should be constant, phi 1 equal to phi 2. Okay, so for this condition to be achieved you have to know the formula for molecular flux, that is all. Also another factor to keep in mind, that d, the diameter of the hole, is much smaller than lambda. What does it signify? It's that basically mean free path, lambda is a mean free path, that means it is the average distance that the molecule can cover between two successive collisions. And so basically it means that if lambda is much larger compared to the hole diameter d, which ensures the fact that while traversing through the hole from one side to the other side, the molecules will not face any collision. That is an idealistic assumption that has been made for the question. Basically because if d is much smaller than lambda, then you can think of it like that this is one collision center and this is other collision point. So in between the distance is, the path distance is lambda. So after lambda distance the collision will occur. But your d is much smaller than lambda, means much smaller than, so basically your d can be just this amount of distance, right? Just hypothetically consider, if this is your d and this whole thing is your lambda, so d is much smaller than lambda. So while passing through the hole you just go from here to here, do not go till all the way till here. So basically you can assume that while passing through the hole, the d distance, there is no collision happening to affect the molecules in any other way. So this is simple flux transfer, as if nothing is colliding with anything or nothing is blocking. So basically this is to ensure that nothing is causing any block or restriction while the molecule flux is passing through that hole. So just that assumption ensures the simplicity of the problem. So this is for simplifying the problem. It's assuming that while passing through the hole, molecules are not colliding with each other. So a simple flux transfer happening without any additional conditions of blockage or restriction. So this assumption is just to simplify our problem. Okay, now the molecular flux formula is, so molecular flux phi is, the formula is 1/4 in C bar. You probably know this formula from the lecture. So this is the standard expression. This is 1/4 in C bar. Okay, so n is the molecular number density, that means number of molecule per volume, and C bar is again the average velocity, right? So that means this is n by 4 into root over of 8 kT by pi m, right? Okay, so then you have to further decompose it, because your P equal to, n kT, pressure relates to n by this, n kBT basically. So your n number density is just simply P by kBT. So you have to also substitute it here, that it is 1/4 into P by kBT into root over of, so this is also kB, 8 kBT by pi m, right? So this is P by root over T into all other constant terms. I mean that these are not varying under this condition of this container problem, because these are the only varying quantity is pressure and temperature from left to right part of the container. The other parts are just the same, because everything is constant here except for this mass, which is also same in both sides, because the same gas is present in both sides of the partition, right? So only P by root over T. That means your molecular flux phi is proportional to P by root over T. So if that is the case, then obviously the equilibrium condition is phi 1 equal to phi 2 at equilibrium, when the flux from one side to other side actually is constant for both the parts. Okay, and then it means P1 by root over T1 is equal to P2 by root over T2, because this is proportional to this. So if phi 1 equal to phi 2, that will automatically mean that P1 by root over T1 equal to P2 by root over T2. So this is the condition in terms of pressure and temperature for equilibrium between both sides of the partition in the container, right? So this is done, and then you have question number 10, which is saying that the coefficient of viscosity for oxygen at STP is given as 1.96 10 to the power minus 4 gram by centimeter second. So remember that this is in CGS unit. So you have to take care of the units later on when you do the calculation. And its molecular weight M is 32, which is in gram obviously. Calculate the collision cross section of oxygen molecule. Okay, so 1.96 10 to the power minus 4 gram centimeter per second is eta. So let me write it down first. Question number 10. 1.96 into 10 to the power minus 4 gram by centimeter second, and the molecular weight, because this is for oxygen, so this is 32 gram for 1 mole, and the pressure and temperature is standard temperature and pressure, that means temperature is 300 Kelvin and pressure is 1 atmosphere. So if pressure is 1 atmosphere, which is also equivalent to you know that this is standardly known that this is 76 centimeter Hg. That means this is the equivalent pressure of mercury of an height of 76 centimeter. So you can write this in terms of, because pressure is equal to h rho g, where h is the height of the element in a column shape you can think of, and rho is the density of that element, and g is the gravitational acceleration. And because we are taking everything in CGS unit for this problem, so all CGS units will be followed. So then I am writing h and in centimeter 76, and rho is the density of mercury, which is just 13.6 gram per cc is the CGS density of mercury. Okay. And gravitational acceleration g is just 980 centimeter per second square when in CGS. So this whole thing is your pressure. So pressure value in CGS standard units is 76 into 13.6 into 980. So this is some value you are getting. Okay. So you are getting 10.1 into 10 to the power 5 CGS unit of pressure. Okay. Now again calculate the necessary parts. Like if capital M is given, then mass of a single molecule will be 32 again in CGS, so I am not converting in kg, so just 6.023 into 10 to the power 23, and if you do this you will get 32 by 6.023 into 10 to the power of 23, which is 5.31 into 10 to the power minus 23 gram. Okay. Now what was the question again? So the question was that calculate the collision cross section of O2 molecule. Now you know that the collision cross section idea comes in between into the formula for lambda, that is a mean free path. So first basically you have to calculate lambda, and then from there on you can get the value of collision cross section area, right? So yeah, what they asked for is probably the area, not the diameter or radius. So collision cross section area, so centimeter square unit is given in the option, so obviously the area has to be calculated. So basically first of all let us write down the necessary formula for this. So till this point you know that formula for eta is 1/3 mn c bar lambda. So here there is a direct relation between lambda and eta. So since you have information about eta you know from the question, m you have just taken out from here, c bar you can get because it is root over 8 kT by pi m, and t and m you already know. And also lambda expression you can write it down further, that it is 1/3 m c bar into n into lambda expression is just 1 by root over 2 n pi sigma squared. So this eta does not have a direct dependence on molecular number density n, so this n and n cancelling out, and you are getting m c bar by 3 root over 2 pi sigma squared. So if you take the collision cross section area, that is your pi sigma square basically, because sigma is your molecular diameter. If you consider that the gas molecules are in spherical shape, then their radius is such that the molecular diameter for each of the molecules is sigma. And how do you get the concept of collision cross section? Is basically this assumption that you think that, let's say in a gaseous system, all the gas molecules are frozen in their position, they are not moving except for a single molecule that is moving around through that sea of the frozen gas molecules. Okay, so that is just to simplify the problem, nothing more. Real situation is not that obviously, but for the simplicity's sake we can think of that all the molecules are sitting frozen in their positions like this. Let's say etc. So I am just drawing a like this is not, do not think of it as a real picture, just picture for a picture I am drawing this. And now another gas molecule which is identical to all of this in shape and property etc, but the only difference is that it is a moving molecule. So this is a velocity v, and this is moving all throughout different points, and this is colliding with the surrounding molecules like that. Okay, so this is the moving molecule colliding with surrounding frozen molecule while traversing through the space, right? Okay, so if that is the case, then what is happening here is that a molecule like this, so this should be a proper circle, so just understand what I am drawing, and then you have another molecule which is just in contact with this. So these two molecules are of same shape, same in size, because gas molecules are all identical, and let's say this is the frozen molecule and this is a moving molecule, and each molecule has a radius of sigma by 2. Similarly, the lower, this one also has a radius of sigma by 2. So just in contact as they collide. So the simplest possibility you can think of is that when the two molecules come just in contact and touch like this, so they are basically colliding. So what is their center to center distance in this case? So this is there, this is one center and this is another center, and this center to center distance is simply sigma by 2 into 2, that is sigma. So the center to center distance between the two molecules which are colliding with each other is sigma. Effectively, this is the effective center to center distance between two colliding molecules. Now just think of it in a way that if this is your moving molecule in blue and is moving and passing through this total sea of constantly frozen in position gas molecules, but when it moves through, it can touch and collide with molecules on any part of its body, like here, 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 here. This is just the points I am trying to mark, nothing else. So on every part it can touch and collide, right? So like for example, if this is sigma by 2, its radius, then it can either collide here, just like I have drawn earlier, and so just one second, I think the charge is not enough. Just let me connect this. Okay, so as I was saying that, let's say you have the moving molecule in this blue dashed lines, and it is passing through all the frozen molecules around it, so it can touch and collide with the frozen molecules anywhere around its circumference, right? So this is just a simplistic picture to get you the idea. Then from any point, the center to center distance, if you will see, this is all the time, this is sigma. Okay, so this is sigma, this is sigma, this is sigma. So like that, from every other direction it can happen, right? From this direction, this direction. So there can be many possibilities. So what will be the effective area within which, if the other molecules are coming in contact with this moving molecule, then they will be the most probable to collide with them. So from there we get the idea of collision cross section, that you can think of it like, so this is sigma So you can think of it as if your collision, there is a sphere of collision which has a radius of sigma. Okay, so like say you can think of that this is somewhat around here from this point, and this. So around this you have, if you just draw a line around, so you can see that all the molecules which has center touching this red line, they will be the most probable to collide with this moving molecule in between, because then their surfaces will touch and they will collide. So this is just an effective idea. This is not necessarily the real picture, but this is just to get an effective idea of the collision cross section. So this sphere is the sphere of collision, and this is the radius of the sphere of collision. So the total area within this is pi sigma square is the effective collision cross sectional area. So whatever molecule that comes within this will be the will be colliding with the center molecule, and therefore it is like effectively taken as the collision cross section area. So however is the case, so basically from here we get the idea that pi sigma square is your collision cross section area A. Now here we have to calculate A, so we directly write down m c bar by 3 root over 2, then pi sigma square we denote by capital A, which we need to calculate. This is equal to eta, right? So then your if this is the case, then A will be just m c bar by 3 root over 2 eta, that we need to calculate. Then m you have already seen that m equal to 5.31 calculated 10 to the power minus 3 gram. So everything in CGS. So this is 5.31 into 10 to the power of minus 23 gram into C bar is basically root over 8 kT by pi m, right? So C bar also you can calculate separately, that this is root over of 8 kBt, which is kb is 1.38 into 10 to the power minus 16 for CGS, not 23, into T is your what was your T, standard temperature and pressure given probably. So let us check once again the question. So yeah, STP, that means it is 300 Kelvin obviously. So this is your 300 Kelvin divided by pi into m is again small m, that is 5.31 into 10 to the power minus 23, and you will get a value of velocity as so I have calculated this already. So this value is 4 you can check for yourself, this is 4.25 into 10 to the power 4 centimeter per second, everything in CGS unit. So this is basically multiply here 4.25 into 10 to the power 4 divided by 3 into root over 2 into your eta values given as 1.96 into 10 to the power minus 4. This is gram per centimeter into second, and this C bar is centimeter by second. So this gram and gram cancelling out, this centimeter comes on the top, okay, centimeter into second, so the second and second will also get cancelled out. So this is just centimeter squared, which should be the effective unit of cross section area. So let us calculate 5.31 into 10 to the power of minus 23 into 4.25 into 10 to the power of 4, okay, divided by 3 into square root of 2 into 1.96 into 10 to the power of minus 4. So this is, you are getting 2.71 into 10 to the power minus 15 centimeter square, or you can say this is 27.1 into 10 to the power of minus 16 centimeter square. Now let us check with the options given. Okay, so yeah, so 10 to the power minus 16 was our order, and the closest answer you have is with C. So it is in the question given in the options is 28, but we have obtained 27.1, but it does not matter because this much little difference may come because of some decimal places up accuracy that you have chosen up to, but this is close enough to tell that this is the answer that we are getting. So this is also correct answer. So correct answer is C. So basically we have covered 10 questions on this. So you can follow up that mostly, as I said in the very first of this session, that mostly the questions are based on the calculation regarding the quantities of viscosity eta, thermal conductivity K, diffusion coefficient capital D, and then the pressure formula P equal to NKT, and the mean free path formula lambda, and the all connecting formula between all those things. Okay, so these are the main things that you need to remember and need to follow, and to solve the problems basically regarding this. So with this we finish this week's lecture, and we'll continue and meet next week.